Hi folks, and welcome to tonight's live session on volumes, mostly by revolutions of solid, or revolving around a certain line. And for other cases we'll encounter a little later, you'll see where we just take an area of some cross section in general. So that's what we're going to do, is we're going to get started by seeing the different lines we can revolve around and how we have the same functions for the most part, and actually get different solutions. So we want to find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line. So in the first problem, we take y equals square root of x minus 1, y equals 0, and x equals 5 as our curves. And then we want to revolve that about the x-axis. So what does that actually look like? Well, first things first, you can always draw the line, or the curve I should say, and get a feel for what's going on. So the square root of x minus 1, that's just taking the graph of the square root of x and shifting it over 1 unit. So we'll say this is the starting point, this is 1. Y equals 0 is one of our bounds, so the x-axis essentially is one of our bounds. And then x equals 5 is our other bound. And so we get this natural sort of bound right here. And what happens is we're going to actually take this, and this is y equals the square root of x minus 1. This value right here, well, notice we can figure that out. Just plug in 5 into that equation and you get square root of 5 minus 1, which is square root of 4, so that means that is 2 for that value. Okay, so what are we going to do with this? Well, I'll actually draw that in blue here. We're going to take this curve and we're going to revolve it around the x-axis. So you get something like this, and then we rotate it and we get this nice little curve going right there. Now what happens in general is we know that this integral will be, and we'll say sum a to b, in the area of the slice of the curve, and we're using x because we're going in the x direction essentially for our curve. So what happens is, when we take a look at this thing, we get some general circle. Oops, don't let your eyes fool you, that's a perfect circle sitting right there. And what we need to do is find out the general equation of this circle. And so what is this radius is the key. Okay, and notice that equation is given by y equals square root of x minus 1. And the area of a circle, so a of x essentially, equals pi, and then I'll put a big question mark here, but that's supposed to be the radius essentially, and then we're squaring it. So what is a question mark? Well, the question mark is just that distance from the x-axis to whatever point occurs on that little curve right there. Well, that point at any given x value is going to be the square root of x minus 1, the quantity squared. So this whole equation, I won't fill in the a to b just yet, but we can have this is pi times the square root of x minus 1, the quantity squared dx. Okay, so that's not so bad. Now with the bounds though, that might be tricky. Well, let's see. Where should we start our bounds? Well, notice the first point in terms of the x values is at 1, and the final point in terms of the x values is 5. And so we have a natural sort of bound here. We go from 1 to 5, and now we're ready to actually integrate this thing. So we pull out a pi, we take the integral from 1 to 5 of, when we square the square root of x minus 1, that whole quantity, we're just left with x minus 1 dx. And so this whole thing equals pi times, well, the antiderivative of x is 1/2 x squared, and then minus 1, so that antiderivative is just going to be x, and then we would take our integral from our bounds were 1 to 5, so we got to plug those back in. So to finish this thing off, we get pi, and then we'll have 1/2, and then we'll do 5 squared minus 1 squared minus 5 minus 1. Notice this will be 1/2, this is 25 minus 1, which is 24, and that is 4. 1/2 of 24 is going to be 12, this is pi times, notice we get 12 minus 4, which is equal to just 8 pi. And so we had a nice solution right there. And that's what we're gunning for, right? Getting these nice solutions in terms of what happens. So now let's change the game a little bit. So what happens when we start revolving about a new axis? Okay, and let's see how that differs. And then we're going to try another one with a whole new axis and gives a totally different sort of frame of mind. So on this one, what's our major difference? Well, we still have the same function. But instead of bounding with y equals 0, we're going to bound with y equals 2. So let's say this is y equals 2. And don't let your eyes fool you, that's a straight line. Once again, we have y equals 2 right here. And then we have this natural bound of x equals 1. So the start of this domain. And then we already know from the previous example, if not, we could set it and find out when it is equal to y equals 2. So you could do, for example, 2 equals square root of x minus 1. You square both sides, you get 4 equals x minus 1. And then we see that 5 equals x. So this point right here will correspond to when x equals 5. But now, so what region have we formed with this y equals 2 and all that stuff? Well, you're actually taking a region like this, and we're going to revolve this around y equals 2. Right? So we're on a region below. So we get something that revolves this way. And so notice we get a nice smooth circular cone there, and then same song and dance. So what we want to find now is a little bit trickier, is what is this radius? So this radius is, and then we got to figure that out. Well, how do we do that? Well, we actually have a couple pieces that we can use. We know that this radius in blue, that has to be y equals square root of x minus 1. So, and then we know that the whole distance, regardless of where I put it, if I go from here to here, that radius has to be 2, right, at any point in time. So this radius that we pointed right in that middle there, that has to be, well, we take the 2 and we subtract off that extra y value that we just had, the square root of x minus 1. So that's going to be our radius. And so that means our area equation, once again, we're revolving in the form of a circle, so it's going to be pi r squared. Well, our r is 2 minus the square root of x minus 1, and we're going to square that quantity. Now, what are the bounds for integration? Well, the bounds for integration, once again, we go from 1 to 5, still in terms of the x's because it's revolving around something similar to the x-axis. So we get pi, but a little bit more fun this time. We have 2 minus square root of x minus 1, the quantity squared. Okay? So, and I see the question, could I do an example like question 13? It's hard for me to pull up the questions on the fly, so I'll try and see if there's a question that you have. Oh, okay, so you want an example that sets up the volume of a solid torus with radii r and little r and capital R. Yeah, I'll go through an example of that. I have no problem doing that. Yeah, just always give me information in terms of the question, and I'll try and pull it as closely as I can. Sometimes I won't know them, so just a little FYI, I like to have them. There's a YouTube live discussion board within every one of my classes that are online and even some of my face-to-face. If you post a question ahead of time in that discussion, more than an hour before, I'll be happy to address it. So just remind me after we get towards the end about the torus one, and I'll be happy I can do that. But in the future, just please post it in that discussion, because it does take me some time to pull that up, and I can't really pull up the web work as easily when I'm doing this. So when we take a look at this problem, where do we go from here? Well, what we end up getting is something like this. So we gotta actually expand this. We'll pull the pi out in front, and then we're gonna square the first term, square that last term, but then we take 2 times the product of the 2 terms just by completing those squares. So we'll get 4 minus 2 times the product would be 4 times the square root of x minus 1. And then we have plus, and when we square the square root of x minus 1, we get plus x minus 1 dx. So hopefully that made sense. If not, let me know. Okay, and we can simplify this. Notice if we take 4 and then we subtract off that 1, we have 3 there. So we get pi times the integral from 1 to 5 of 3 and then plus x, and then minus that 4 square root of x minus 1. Well, we'll deal with that integral separately. So we'll do 3 plus x, and then we have that dx, minus, and then we'll have a 4 pi, the integral from 1 to 5 of square root of x minus 1 dx. Okay, so when we take a look at this, the integral is going to be a bit tougher. Not too bad, but it's still slightly more difficult than what we had before. So we have pi times, notice you have 3x plus 1/2 x squared. Evaluated at 1 and 5. In the second case, though, minus 4 pi, we'll need to use a u substitution. U equals x minus 1. That means du equals dx. But that means we actually need to change the bounds here. So you plug in the bounds into our u equation. So you plug in for x. So when you plug in, you get 1 minus 1, which is 0 down below. And then you get 5 minus 1, which is 4 up above. And notice this becomes the square root of u du. Or a little more simply put, we can rewrite that as u to the 1/2 power du. And that way hopefully we can see this a little bit easier. So now moving forward from here, hopefully I can erase these little pieces in terms of what's happening. So now moving forward, what do we have? So you get pi, and then we plug in. So we get 3 times the quantity 5 minus 1 plus 1/2 times the quantity we have 5 squared minus 1 squared. Okay, everything's hunky-dory there thus far. Minus, we have 4 pi, and then our antiderivative of u to the 1/2, that'll be 2/3 u to the 3/2 evaluated at 0 and 4. Which, what does that mean? Well, it means first off we can simplify that first piece. So you get 3 times 4, which is 12, plus 1/2 times, this will be 24, so that's another 12. So 12 plus 12 makes 24, so we have 24 pi. And then notice 4 pi times 2/3 makes 8 pi, so minus 8/3 pi. And then 3/2 power, that just means the square root. And then we cube it. So square root of 4, the quantity cubed, minus square root of 0, the quantity cubed. Well, that'll be 2 cubed, essentially. So you get 8 right here. And so that'd be 64 over 3. So you get 24 pi minus 64 thirds pi. You know, that's good for a final answer. You can brush it up a little bit more if need be. I mean, you get a common denominator, it's not too hard. So if you were to do that, you just take 24 times 3, which is 72. 72 minus 64, so that would be 8/3 pi. The main thing is, it's a different answer, right? So it's different than the 8 pi that we had before, and it's just showing you it does depend upon what axis we're kind of revolving things around. And I want to illustrate it one more way. So both of these, notice this curve was kind of smooth. They were always touching the axis they were curving around. That isn't always the case either. So you can have another scenario where you actually have the same curve. We'll go back. It's the same actually curves involved with the first problem that we saw on the previous page, but now we're going to revolve about y equals -2. This becomes a whole different problem altogether. So what happens? Well, so you get, it's the same curve being bounded, so you still have 1 and 5, and we still get that little shindig going on right there. But now the big difference is, and we'll try and I'll kind of ballpark this, we'll say -2 is right here for the y value. This is the axis we're going to revolve around. So what does that mean? Well, first off, you have a distance from here to here of 2 units. So that means on the bottom end we're going to have another solid piece of distance 2, but this is not going to be included. So I'm going to kind of hollow this out. You see this little cylinder right here? We're going to have to take this out of the volume. And then what we're going to have to do is we're going to revolve this thing around. So it kind of looks like a bowl with almost a hole in the middle, essentially. Let's kind of do this. So you get this curve and it comes around here, and then we have this curve going right there. And then in general, what do we want? Well, we're going to have two things, and this is called the washer method that we're going to use. You have a curve going right here, and then it kind of segues back on out. But the radius that we're looking about, this is y equals -2. So you have a radius first to this outer portion. Okay? And remember, this is y equals square root of x minus 1. But we're going to have to take away this smaller portion right here. So how in the heck do we do this? Well, this is the washer method. So the washer method says basically you have some a to b bound that really won't change, and you have your area of your first equation. So I'll put a sub 1x, and then you're going to subtract off the area of the second equation. Now that's a more general approach. Your book would probably tell you in terms of it being pi. Well, this is more general in terms of, it depends what the sort of cross section you're taking out. Well, to illustrate, let's do the outer. And so this one's your outer surface, and this one's your inner surface. So what happens with our outer? Well, the outer radius, let's take a look. Because we're revolving in a circle, it's going to be the pi r squared. So what's that outer radius? Well, notice we had that distance of 2 here. So it'd be 2 plus the extra distance from here to here would be the square root of x minus 1. So you get 2 plus the square root of x minus 1. So that means this a1 of x, when we did that, it needed to be the integral from, notice we're 1 to 5 again, and we get pi times this radius, so the 2 plus square root of x minus 1, take that quantity and square it. That's the outer. Now the inner function, notice that is just a distance. We said it's a cylinder, so that thing is just 2. Alright, so inner radius never changes, it's always 2. So this equals just 2 all the time. So that's pi times 2, the quantity squared. And all this thing is dx. Oh, let me put parentheses there, put parentheses there, and now we have the dx. Okay? So now moving forward from here, what do we have? Well, taking a look at this, we can simplify that a little bit. 1 to 5. We can pull the pi out of both terms, and so hopefully make our lives a little bit easier. Notice we'll get 4 plus. We want to take twice the product of the two terms, so that'd be 4 times the square root of x minus 1. Plus, and we want to square that last term, so we get x minus 1. Minus, and notice we had 4 pi, but so we're going to actually take off we've already factored the pi out, so it's just going to be 4 here. and we can do some brushing up. And hopefully a lot of this will look familiar. So notice the 4 minus the 4, those things cancel. So we're left with basically x minus 1 and that 4 square root of x minus 1. So we can have pi times the integral of 1 to 5. We'll separate these two things once again. Square root of, oops, I'll do 4 pi. And then you have square root of x minus 1 dx. And then plus the integral from 1 to 5. We have a pi out in front, and that's all we need. And it goes x minus 1 dx. Recall we did a u substitution a second ago. And just so you can see what happened to this integral, notice we have a 4 pi here, right? So you have a 4 pi square root of x minus 1. What did that become? Well, at the end of the day, it looks like we had an 64/3 pi is what that became. So in this case, the only difference is it's going to be a positive versus I think the other one we were subtracting. Yeah. So we had a negative 64/3 pi. So this whole thing, with the 4 pi included, is 64/3 pi. And if you want to see that integral done again, we can do the u substitution again, that's fine. And then this next part, hopefully this is becoming a little more familiar. We get 1/2 x squared minus x, evaluated at 1 and 5. So this equals 64/3 pi plus pi times, we get 5 squared minus 1 squared minus the 25 minus 1. So 5 squared minus 1 squared, oh, I forgot the 1/2 there. 1/2 5 squared minus 1 squared. So once again, that's 24, and 1/2 of 24 is 12 minus 4. So that becomes 12 minus 4, which is 8. So we are left with 64/3 pi plus 8 pi. And so that'd be 64/3 pi plus another 24/3 pi, and so that makes 88/3 pi, I believe. So something like that. And so notice this one's the most, and it seems to stretch out the furthest. There's reasons behind that, okay? So if there's any questions, let me know. I really wanted to illustrate how we can have the same sort of function involved every time. Depending upon the axis we rotate around, you have to use completely different methods in terms of whether it's a washer method, whether you're looking at it from a different perspective and just subtracting it, or just using your normal, just using that function as one end. So it always depends upon this axis that we're rotating around. It makes a big difference. And notice each time we drew the graph. So understanding your graphs is going to help you a long way too. In this next case, you have y equals x squared and x equals y squared. So what the heck is happening there? And we'll have about y equals 1. We'll talk about that in a second. So first off, y equals x squared looks something like this. Okay? And then let's draw in pink x equals y squared. So you get x equals y squared looks something like that. Now how can we figure out when these two things equal? Well, easy way to do that is just make a substitution. You have y equals x squared, so you have x equals x squared squared. So x to the 4th equals x. And so most people just divide both sides by x and say they're done with it. It isn't quite that simple. So you can subtract x from both sides. You get 0 equals x to the 4th minus x. So say you didn't know the graph, this is what we're doing here. So you can factor out an x, so this makes x and x cubed minus 1. And so what we get for this, you get x equals 0 or x cubed minus 1 equals 0. You can solve for that. Actually, you can factor x cubed minus 1, by the way. If you don't know how to factor it, it's x minus 1 times x squared plus x plus 1 equals 0 is the way to factor it. And notice you get x equals 1 as the solution. This one, the root is 1 plus or minus the square root of negative 3 all over 2, or better yet, 1 plus or minus the square root of 3i over 2. So you have a complex number, so that's not going to play a role here. So we don't have to worry about that. So what it's telling us is this value right here actually coincides with where we want to revolve things around, y equals 1. And what happens is all this other stuff just kind of goes away. We really don't need it. The only region we're revolving around is the region that's enclosed. So we have this gone, and this, oops, did a little too much there, gone. So you have that and that. And so notice this is similar to the others. We're always dealing with x here, since we're revolving around something that looks and behaves like x. The tricky part will be how we mess with these curves and setting that up. So notice our bounds of integration, we have 0 and we have 1 are going to be the things that we're working with in terms of x. But it's a little bit more interesting in terms of what equations we use here. So keeping that in mind, another way we could have written this. So we have y equals x squared. That looks good for this part, and that's the bottom equation, y equals x squared. If you didn't know it, you found their intersection point, plug in a number between 0 and 1, you'll find out which one stays on top, which one stays down below. The second one, remember this is y equals plus or minus the square root of x, but since we only care about this region enclosed here, the only thing we need is to take a look at the y equals positive square root of x, because it's above the x-axis. So keeping that in mind, what actually happens? What curves, what are we looking at here? So there's a few different regions we need to break this thing up into. So I'm going to break it up. We have that with the red, and then we have, I'll do orange here, and we have this little orange slice. So how do we do this thing and actually figure out what that region is in terms of the radius? Because what we really want to revolve is from the orange to the black. That full line there would be a radius, but then we'll just subtract out the orange. Okay, so this area we'll begin with will be the area of this slice, and then what we'll have to do is subtract out the area of that bottom slice. So what is this radius first? And then, since we're revolving in a circle, what is that second radius? Okay. I think the easiest of all of them is the second radius. Okay, so the second radius, notice that's just a distance to that line y equals x squared, so that has to be x squared. The second piece is a little bit trickier, because essentially what we want is we have a height of 1, right? But so how far are we going down? Well, it looks like, well, for example here, this distance on that piece right there, that distance should be the square root of x minus x squared, right? And then the other distance, what should that be? Well, that should be 1 minus the square root of x. Okay? So essentially that last piece, oh, I was saying the second radius, I'm sorry, I got confused there myself there. That second radius isn't necessary. The x squared itself isn't necessary. My apologies. The radius that we needed is basically this distance, the square root of x minus x squared, right, plus that 1 minus square root of x. So an easier way for us to have written that for that first radius would have been just we would have had 1, the square root of x is cancel, we would have had 1 minus x squared. In the second case, that smaller radius, which is what we're taking away because we're revolving around this circle, so I should actually draw the figure. It does help. So drawing this out, we get this outer radius going on here, and we get this inner radius kind of taken out, just like so. And then you'll have that whole thing finishing up. So the one that we're looking at for the slice, this is the 1 minus x squared will be the outer sort of radius now. I know that seems counterintuitive, but that's what we're looking at. And the inner radius will be that 1 minus square root of x that we just discussed. Okay, so when we find our area, and we remember we go our outer minus our inner, so we'll take our pi, our integral goes from 0 to 1, and then we want to take 1 minus the square root of x is our inner. Oops, I'm doing that the opposite direction. We want our outer first, so we want to take 1 minus x squared, that's our outer, and we're going to square that. And then we subtract off the pi times the inner radius squared, so that'd be 1 minus the square root of x, the quantity squared. In all this, we take our derivative with respect to x. Okay, so taking a look at this thing, what do we get? Well, we get the integral from 0 to 1. We can pull out the pi. When we square that first term, we get 1 minus 2x squared plus x to the fourth minus, we've already pulled out the pi, but remember we're going to subtract all this quantity, so it goes 1 minus 2 square root of x plus x, and we have a dx sitting right there. And then we need an extra parentheses as well. Okay, so we got a whole bunch of stuff. The good news is the 1 and the 1 over here cancel, so the life is a little bit easier. It's not all hunky-dory, but it's good enough. So we can rewrite this. When we take the inner derivative of 2x squared, that's 2/3 x cubed. The antiderivative of x to the fourth is 1/5 x to the fifth. And by the way, we need all this to be multiplied by pi once again. That's something that we can't really forget about here. 2 squared x, notice minus and a minus, that's going to make a plus. So that'll be useful. You have 2 and then x to the 1/2. So when we take that antiderivative, that'll be 2 and then times 2/3 x to the 3/2. And then we have a plus x, so that'll be minus now 1/2 x squared. That's a lot of work for just a little bit. So now moving forward, what do we get? Oh, this is kind of boxed off. We'll have pi. Notice when we plug in 0 to every one of these, you're going to get 0. And then when you plug in 1, you're just going to get the number 1 returned. So what this becomes is just 2/3 plus 1/5 plus 4/3, it looks like there, and then minus 1/2. So I don't know much, but I could probably brush up 2/3 and 4/3. That's going to make 6/3, which is just 2. So this is pi times 2 plus 1/5 minus 1/2. And so that becomes 5/10 and 2/10, so that make -3/10. So this is pi times 2 minus 3/10. And so that'd be 20/10, which is minus 3/10, should be 17/10 pi. And that's our final answer. Okay, so that was a bit of a tricky one, but hopefully you can see, hey, we're just messing with the radius. I actually didn't draw the picture right away, and that kind of caused a little hiccup there. But so hopefully you saw as soon as we draw on the radius, kind of swerve it around there, things work all hunky-dory. So now, moving this around, find the volume obtained by rotating the region bounded by the curves xy equals 1, y equals 0, x equals 1, x equals 2, about the line x equals -1. Oh, okay. So I have a question that says, hey, can you take a look at how you determine the inner and the outer equations? That part is confusing me. Sure. So I'll kind of erase real quick what's going on here. So that's the trickiest part, I'd say, of setting. You know, all this stuff is just, it's mainly a setup. How do you set these things up? So remember, the top equation is y equals square root of x, and it's positive square root of x. So what happens is we're going to mimic this thing over to the other side. Okay, I'm going to try and draw in a different color. And for this portion that's in black, we've got this shape, and we have that radius. Now notice that radius could go on the other side as well. I'm going to just write it on this side, but we'll try and figure out what that thing is. Okay. Over on the other side, if you notice, if we took it all the way to that point down and didn't even worry about touching that bottom curve that was shaded in blue at first, and when I'm mean shaded in blue, I'm talking this curve right here, that's the y equals x squared. If we took it all the way down, went beyond the curve in blue, that'd be just 1. But what happens is we got to stop when we hit x squared, and that's the extra distance that we have to subtract off. So this is the outer radius. Okay. So now it's time for the inner radius. What the heck is that going to be? Well, notice that inner radius, we'll draw, let me do it in purple. Okay, so that inner radius is that distance right there. So what the heck is that thing going to be? Well, notice the distance, if we were to take that purple line all the way down to the bottom, that would be 1. But we didn't, we stopped short. And so it would be where we hit that kind of reddish curve. And what happens with that reddish curve, or pinkish, or whatever the heck you want to call that color? So at the end of the day, that distance should be the square root of x. And so this has to be your inner. Oops. Oh, I didn't mean to do that. Oh. Well, shoot. Okay. Might take a couple seconds. Okay. There we go. Back in action. Alright, so the inner, let me try not to hit it this time, is that 1 minus square root of x. Now remember, all we needed to do is take pi times our radius squared. So you take pi times, and that's, so this is our outer area. And this second one is just our inner area. So that's all it is. It's really tricky to set up a lot of the times, but you just got to try and find those distances. Now, actually, when I started the problem, I was looking at, for some reason, I don't know why, but I was revolving around the x-axis. And so that's where you saw a little bit of a screw up. I'm starting with that. I forgot about the fact that we're revolving about. The key is y equals 1. As soon as we put that in, this became a bit harder of a problem. But I'm glad you're asking the question. Hopefully, does that make sense? If not, I can try and clarify a little bit more. And then hopefully this next example will show you we're going to even revolve around a different sort of axis, or axis I should say. And so that's the trickiest part, is setting these things up and trying to figure out where the heck are we revolving around. So I don't see any more questions, so hopefully if not, we'll kind of move on to this next one. So in this one we have y equals 0. So that's just the x-axis. We have x equals 1 and x equals 2. And what that curve looks like, so y equals, so this xy equals 1, you could write it as y equals 1 over x is pretty familiar, or you could write it as x equals 1 over y. Right? But at the end of the day, you get this curve that kind of swoops on down and goes something like this, and all that jazz. But what we're looking at is, here's 2 of your bounds. But the tricky part, what makes this a bit harder, is that this is similar, we're going x equals -1, and that's the axis we're revolving around. Okay, so if that's the case, and we're revolving around this axis, then it's going to be different in terms of the bounds. We can't put it in terms of the x as of yet. Soon enough we'll learn a shortcut and how to do this and put it in terms of x, and everything will be hunky-dory. But For right now, we don't really have that. And so we'll have to figure out a nice little way to set this thing up. And in terms of what we're looking at, so I can erase that part of the curve and this part of the curve. And this is all we're really focused on. And as we mentioned, we have to put it in terms of y. X equals 1 over y, because we're revolving around something similar to revolving around the y-axis. Okay, and so it has to be in terms of y. So now, what the heck happens? Well, this thing, notice you'll get this little curve right here going on. And then you also have this curve down below, but we don't care about the top and bottom. What we care about is a slice of something in the middle. So say you took a random thing in the middle and kind of took the slice right there. What would this sort of circle be? And so we have some sort of circle. What the heck is that going to be? And now this means we're going to be looking for a function in terms of y. Okay, so you have x equals 1 over y as that equation. Notice this is x equals 1 to x equals 2, so that might cause a little bit of problem, but not too bad. And now we need to think about, okay, so what's going to happen in terms of our radius? How do we get an equation for that radius? Well, notice if you take a close look, we have a distance here, and that distance is 1. Okay, and then we got to slap on another distance right here. So what is that distance? Well, that distance is just given by 1 over y. We can always get the x value in terms of 1 over y right there. So if we take these two things together, add them up, that's going to be our radius every single time. Okay, so first off, our a of y equation in this case will be pi times, our radius is 1 plus 1 over y, and then we square that. Okay, any questions on that thus far? But this is not our full equation. This area y I started with right there. Notice we stop at x equals 1. So with that in mind, this is our outer area, or so I should write area of y involving our outer radius. So maybe make an a sub 1y, and now we need an a sub 2y, and this one involves the inner radius. Whoops. So on our second piece where we involve the inner radius, what does that look like? Well, notice we stop right here, so we go this distance and then another bit of that distance. So this distance is 1 and this distance is another 1. So that means we got to go pi times 2, right? Because 1 plus 1 makes 2, or constant functions, 2 squared. So in this whole song and dance, what do we have? Well, we can factor out a pi, and we take the integral. We'll talk about our bounds in a second, actually. And then so we take our outer radius, so that's 1 plus 1 over y, the quantity squared, minus 2 squared is just, well, I'll actually write it out, 2 squared for now. And then we have a dy. What are our bounds? So where are we going with our y values? Well, notice you start with the y value. What is the y value right here? Well, the y value is 0. So y equals 0 right there. So that's our lower bound. And I want to go back, it trips people up in terms of how high we go, right? So we're going to be looking right there. If you look back just a second ago, when we took our integral all the way out, notice we kind of finished at some different spots. So for one of them, we went from 1 to 5. Why did we stop at 1 and why did we stop at 5? Well, those were the endpoints of how far out we went. Well, how far do we go in terms of the y value? Well, if you notice, the highest y value would occur when x equals what? 1. So the other value, we get x equals 1 over y would become 1 is for our x value equals 1 over y. So that means y equals 1 over 1, or just y equals 1. And so simple as that, we have our solution. Now here's a check actually if you've made an incorrect kind of statement along the way. If you ever have a negative for outer or inner, if you ever have, doing the subtraction here, if you ever get that to be a negative value, all of a sudden you know you made a mistake, because volume has to be a positive number. So keep that in mind too. I mean, just setting these things up, it can be tricky, but that can be a giveaway in terms of how you set your integral. And you might be thinking, oh, it might be where our x value equals 2, right? But what you'll find is that this is 2 and then this would be 1/2. Okay, so that wouldn't be extending the integral to as far as it can go. You'd have to extend the second part of it. So moving forward, you get pi, and then you take the integral from 0 to 1. You get 1 plus, another way to write this, 2 times 1 over y, 2 times 1 times 1 over y, which is 2 over y, plus 1 over y squared, and then minus 4 dy. Another way for us to write this that might be a little bit simpler for a lot of folks is the integral from 0 to 1. You get negative 3, and then this will be plus 2y, and then we have negative 1 right there, and then plus y to the negative 2. And then we want a dy on that thing. Okay. Oh, and the 2 y to the negative 1, you might like this better. And so that might seem a little bit nicer. Did I do that right? Did we get xy equals 1? We took everything. Sorry for the hesitation, folks. I'm just taking a look real quick to make sure that everything's set up all right. And did we want that about the line x equals negative 1? Oh, I actually apologize here. I actually needed a second area. Notice when I did the outer minus inner, that 0 is not correct. So that's actually, notice this first part, we have 1 over y kind of sitting on top of something at 2 1/2. So this actually needed to be, this integral needed to be from 1/2 to 1, and I'll kind of explain why. So you have this sort of sliver right here that's being rotated around to the bottom piece and to the top piece, so that should go to the top piece there. That sliver is basically a cylinder with the hole cut out. So the 0 to 1/2, I forgot to add that in. My apologies. So as I said, this can be very tricky. We're going to find a better method on this one soon enough. So I'm trying to choose some trickier problems so you can see how these can work out. So this 1/2 to 1 is the integral. Notice that's where we're running the curve, and I'll draw it back in pink. Right here. Because our y value starts at 1/2 for that curve, and then it goes up to 1 for those y values. For the other portion, we want to see what's our rightmost and what's our leftmost. Well, our rightmost is just x equals 2, so this would go pi times let me actually write it. So that's 2, but notice we have a distance of 1 right here. So that'd be pi times 3 squared minus pi times, and then the other distance is 1, so it'd be pi times 2 squared. And that integral goes from 0 to 1/2, and all that's dy. So that's that bottom portion. My apologies. I know that can be confusing sometimes, and it caught me for a second there. The hesitation, actually, you saw the reason why I knew something was up. In terms of the 0, I knew the antiderivative of 1 over y would equal natural log of absolute value of y. And I know that natural log of 0 doesn't make sense. So there was one extra piece I knew we were forgetting about, and that's where the 0 came in. So that'll actually, this will set up the whole integral. We'll be good to go. So notice this second piece, well, actually, let's rewrite this thing. So you can write pi times the integral, or from 1/2 to 1 of, we had same sum of dance, it goes 1 plus, let's write it as 2 times 1 over y, so you can see that natural log of y a little bit more clearly. And this 1 over y squared minus 4 dy. But then the second part that we're going to be adding in is from 0 to 1/2. We can still pull out a pi in this case. And what are we left with? So when we pull out that pi, we have 9 minus 4, and so that makes 5 dy. And so this will be a little bit nicer in terms of getting us towards our answer too. So notice 1 minus 4 makes negative 3. This is plus 2 times 1 over y, and then plus, you might want to write that as y to the negative 2. So that becomes pi times negative 3y plus 2 natural log of y. And then we have, that'd be minus y to the negative 1, and that's where the minus comes from when you have that. And so that's evaluated from 1/2 to 1. In the second portion that we're going to be adding in, so you get plus pi times, it just goes 5y, evaluated from 0 to 1/2. And taking a look at this, what happens? Well, you got to plug in the bounds. The first one's going to be a little bit trickier. So you get pi times negative 3, and then it goes 1 minus 1/2 plus 2 times, you get natural log of 1 minus natural log of 1/2, which we can simplify that a little bit too. In our next case, we have that minus y to the negative 1, so that'd be minus, so it goes 1 minus y to the negative 1 is 1 over, so 1 over 1/2. And then plus pi times, well, the 5y, that becomes 5 times, plug in 0, that's just going to give us 0, so 5 times 1/2. So this whole business, we get negative 3/2 for the first part. The natural log of 1, that thing is 0. And then you have negative natural log of 1/2. That is negative natural log of 2. Not saying you have to do that part, but so that makes it natural log of 2. And then this becomes 1 minus, and so that's 2. 1 minus 2 is negative 1, and negative 1 makes a positive 1. So you have pi times negative 3/2 plus 2 natural log of 2, and then we have plus 1. So that's a lot of craziness there, and then plus another 5/2 pi. Okay, so negative 3/2 plus 1, that makes negative 1/2, and notice that's going to be times pi. So negative 1/2 times pi plus 5/2 times pi. Notice this whole thing equals 2 pi plus 2 pi natural log of 2. Okay, a lot of craziness going on there. I understand, but you can see how we work all this out and we build this. What's going to be nice soon enough is we're going to get what's called the shell method, and I guarantee that you would rather do this problem using that shell method. Basically, that's what we're building to. You can see how some of these can be extremely difficult to set up. The shell method would make this easy. We basically take a 2 pi times whatever that radius is, essentially, that in this case it would be x plus 1 times our function in terms of x. So it'll be where we set up an equation in terms of x rather than in terms of y. So life would become a lot easier in that case. So hopefully that makes sense on this one, and we'll keep on moving along. So for this one, we're starting to get a little more abstract, and that's what we want to tend to do if possible. So find the volume for a frustum of a period with a square base. That's key, square base of side B at the bottom and square top of side A. So what happens is we have a few different ways to set this up. We have our height being h, and you can pretend that we were projecting this thing. So say I have this line right smack dab in the middle of that thing. What does this look like? Well, you get some point here, and then you match over to some point out here. And what's the drawing going to look like? Well, it's going to be a straight line. Okay, but if it's right in the middle, notice what does that do when we project that on over here? Well, that takes this distance. It's a on the outside, so that would be a over 2. So that means that this distance right here has to be a over 2. In a similar manner, we've taken this distance right here and we've halved that because it's a square. So that's b over 2. So that means this distance right here is b over 2. Now I know I played it on the side, but there's a reason for that. There's a method to the madness. So we can have things in terms of x. That might be a little, oops, that's b over 2. And so now our whole height of this thing, so from bottom to top, that should be h. And so that's why we put h for that. And we'll talk about the area of our cross section, how that looks in just a second. But first, what we need is the equation. What is this equation? Okay, so notice the coordinates of that point right there would be 0, comma a over 2. And the coordinates for this point would be h, comma b over 2. So when we get this equation, we need the slope. Well, the slope of this, because it's just a straight line, we take b over 2 minus our a over 2, and we take that and we go h minus 0. That's just our slope formula that we have. An easier way to state this is multiply both the top and bottom by 2, so you get b minus a all over 2h. Now notice our y-intercept is a over 2, just by the way we set it up. So that's where we had some choices. We could have started by setting it up at b over 2 if we wanted and try and build up the other way. Either way works. But so in regards to this now, this means our equation of the line, just by using our point slope formula, you get y equals b minus a all over 2 times x, 2h, I'm sorry, all times x plus a over 2. Wowzers, right? So what happens with this? Well, when you think about it, what do we need to do? Well, we have some random point here. We know what this distance is. This is just the equation of the line that we're going to plug in. But what happens is we're going to take a slice. If you take a slice at any point in this frustum, you get a square. But notice that square, we only have a sliver of that, and so we're only worried about this. So in order to do that, we're going to need to double it and then square that double. Okay, so this distance right here would have been the b minus a all over 2h times x plus a over 2. So we're going to need to double that. So what we get for our integral, and notice our integral goes from 0 to h because it's on our side. So we double that, so 2 times b minus a over 2h times x plus a over 2. Right? That double has to be times the whole thing. Remember, we're taking this in each direction. That's basically what we're doing. We're taking a square out of this thing and kind of going on up. And they're getting smaller and smaller squares and larger as we get towards the bottom. So, and then we need to take that and we're going to square it. So let me get rid of that piece. So this and then dx. And notice it's a square. That's why I like this, because it's a different slice in terms of what we have happen here. So if you multiply that 2 on through, we can actually simplify this a little bit. And notice there's no pi in this one either. So you're left with b minus a over h times x plus a, and then we take that quantity squared and we find dx. So in order to do this, we'll first square it. So you get 0 to h. We get b minus a over h, the quantity squared, x squared, plus 2 times b minus a over h times x plus a squared, and then we want dx of all that. Well, moving forward from there, we'll go 1/3 x cubed essentially times that constant. So 1/3 b minus a over h, the quantity squared. I know that looks nasty, but that's okay. And then this will be x cubed. That's the x cubed part. Plus, notice you have 2 times b minus a over h. And I know I moved the 1/3 out in front. I'll leave the 1/2 here. 1/2 x squared. And then plus, notice a squared is just a constant, so that's a squared times x. And then all this whole piece of junk, what's going on there? We take the derivative, we've already gotten that, we go from 0 to h. So what happens at the end of the day? We get b minus a over h, the quantity squared. We have a 1/3, so I'll put it this time here. So we have 1/3, and then we have h cubed. Okay, plus 2 times b minus a over h times 1/2 x squared. Well, we'll plug in an h for that, so we get h squared. Oh, by the way, the 2 and the 1/2 cancel. And then we have plus a squared h. A lot of work, right? But when you look at it, this is going to have an h squared. And so what you're left with is you'll have a b minus a, the quantity squared, times 1/3 h. Then you'll have plus this h squared. The square will cancel off with that h, and you're left with b minus a, the quantity h, times the quantity h there, and then plus a squared h. And so what does that become? Well, the first part will have 1/3 b squared h minus 2/3 abh plus 1/3 a squared h plus bh minus ah plus a squared h. Notice you have an a squared h there. You have a 1/3 a squared h. So that makes 4/3 a squared h. In fact, you can factor out an h out of everything, to be honest with you, and that probably look a little bit better. So you'd have h, and you have the 4/3 a squared. Okay. Then we have, what do we have? We have a 1/3 b squared h. So plus 1/3, we've already factored out the h, so 1/3 b squared. Okay, so that part's gone. Minus 2/3 ab. That takes care of that part. And then plus b and minus a. I'm sure that's exactly what you were thinking ahead of time, right? But so what it's showing you is that how we can build to these general sort of solutions, even though it doesn't seem like we have a nice solution sitting there. So now you can plug in any a, b, and h, and you have a solution within a matter of a few seconds. So hopefully that makes sense in terms of how that one works out. Let's see now. We want to find the volume of a pyramid with height h and a rectangular base with dimensions b and 2b. So we'll have some sort of pyramid. And what we'll do, though, is we'll pretend there's an axis of symmetry right down the middle. And we know what happens, right? We have that this side would be something like 2b, and this side would be something like b. Now, what probably be the easiest is to break up the 2b, and how we set up our equation. We have a few options here, and we have a height of h. So notice the relationship of any sort of spot we go for, you're going to have this thing is cut right in the middle if you want to cut it this way. Okay, so if that's the case, if we start and we put this point corresponds to that right there, we can build to some other point at the bottom, right? So, but we want to extend all the way out here. Okay, so what happens? If we extend that out, the height is going to be h, that's the x value. And then what is this sort of height that we're going on here? Well, the height in that case, notice we've halved it, so we'll have this value be b because the total distance would be 2b. Okay. So now we have an equation. We have 0, 0 as one of the coordinates. And we have h comma b as the other. And so we can find the equation. And so first we find the slope. Well, that goes b minus 0 all over h minus 0. So that's b over h. The y-intercept equals 0. Hence our equation for the line is y equals b over h times x. Okay, so taking a look at this, what happens now? Well, when you look, we're taking a random cross-section. But this is only half of that distance, so this would be, there's your other half, and we're kind of extending out and back in. So this distance right here is our equation distance, but we'll need to double it And to find the area, that should be just the regular distance, what's involved there for the equation. So this area formula, essentially it'll be 2 times our equation squared. Right, because just like you see 2b times b, in any general place we have what that is. So in other words, we have a of x equals 2 times b over h squared. Now notice the last time we had the 2 on the inside, right? This time we won't. We have it on the outside because it's just one of those sides is doubled. Okay? Versus the square have both of them being doubled. So this means, and by the way, this isn't the only way. There's all sorts of different ways to set these things up. So, but our integral goes from 0 to h because h is our final x value. We get 2 times b over h x, the quantity squared. Easier way to pull that out and take this antiderivative, we get 2b squared over h squared, integral from 0 to h of x squared dx. So that equals 2b squared over h squared, and then we have 1/3 x cubed evaluated at 0 and h, since that's the antiderivative there. Plugging in our bounds, we get 2b squared over, and we can pull the 3 down with that h squared, and then we have just essentially h cubed. So notice the cube crosses off with the h squared, and we're left with our final answer of, well, let's write it this way, 2/3 b squared h, and that is our final answer. Okay, so that's all I was planning on in the first part. But I think there was one last question involving a torus, right? So let me know if not. I'm happy to, if this cleared it up. But so let's say we have a torus of radii, let's say 20 and 5. So what does that look like first off? It's a donut, essentially. And then don't let your eyes fool you, this is a perfect circle here. And so they say that, hey, this radius right here, that has to be the 20. And then you have another radius sitting right here to here. This would be 5. Now in general, what we're looking at is you can change this 20 and 5 to any capital R and little r that you need. But this is a general idea. Find the volume. And so the key lies in the center circle, where you center your circle at. So circle centered at HK. Of radius little r, we'll say. What does that look like in terms of its equation? Well, in general, you'd have x minus h, the quantity squared, plus y minus k, the quantity squared, equals little r squared. Well, in this case, our little r, so our smaller circle, has radius 5. And then we can set this thing up in such a way we have a lot of freedom, just like the other problems. It's all dependent upon how we set this thing up. So what we'll do, though, is we'll let this circle have radius 5, and then we'll let the center of that circle be 20, which represents our other radius. So that means this circle, and assuming this radius is 5, this would be x. Notice we've shifted the x 20 units, so minus 20 squared, plus, have we shifted the y any? Well, no, we left y at 0, so that's the beauty of this, is we'll make our life a little easier. So plus y squared equals, so this would be 5 squared. Now here's what makes it hard though. If you notice how our torus works, we're going to have to revolve around the y-axis. That means we have to solve in terms of y. So we get x equals essentially. So that means x minus 20 squared equals 25 minus y squared. Or you could leave it 5 squared minus y squared, whichever you prefer. Here's the tricky part and what happens. So you get, when you take the square root, x minus 20 equals plus or minus, what the heck happened here? So you get plus or minus the square root of 25 minus y squared. Well, here's the deal. The positive part, remember this is essentially going right half and left half. This is x equals, notice we'll have to add 20 to the other side to finish it off, so you get 20 plus the square root of 25 minus y squared. That's all that is. On the other side, I'll do this in pink. Well, actually pink probably wouldn't be a good choice. We'll go purple. Can you take a wild guess as to what might happen on this side? What would that equation be for the left hand portion? Let's see if you get it. X equals, if the other one was 20 plus the square root of 25 minus y squared, which one haven't we used? Starts with 20, and then the only other portion that we haven't used is in the meantime, yeah, it's exactly, it's the 20 minus the square root of 25 minus y squared. So that's the only thing that we have to worry about. And now we will have to worry about our bounds of integration for a little bit. We'll deal with that when the time comes, but we're gonna, so we have this portion to this portion, and we'll worry about that in a second. But in terms of how we set up our formulas, notice the way we're revolving, we're taking this portion on the outside and looping it all the way around, right? But then we're going to take this, and so that's the outer portion. This inner portion, we're going to need to subtract. And don't let your eyes fool you, that was kind of a circle as best as I can do it there. You're actually taking out this inner circle, essentially. So it's basically the same song and dance as to what we've been doing. We have an integral. We'll figure out what the bounds are in a second. The outer portion is the 20, so we take pi times 20 plus the square root of 25 minus y squared, the quantity squared, minus, and then we go pi times 20 minus the square root of 25 minus y squared, and then we take that quantity squared. Okay, and so this whole thing, we go dy. Now what about the bounds? So the integral isn't bothering you. If you just want to show the setup, yeah, I'll go through the integration process. It's not a big deal. But yeah, I want to make sure we get the setup all going here. So now we got to think about where our y value is ranging from. Well, notice we start at the bottom end. We go, our y bound goes as low as, well, if the radius is 5, it goes down to -5, and then the same thing up here, it goes +5. Okay. Now there's another little trick you can do to make your life a little easier, whether it's even or odd functions. So you actually have this scenario here where you have an even function, and so this integral, we can pull the pi out obviously from both pieces, but you can also change the bounds, and that's a beautiful thing too. You can go, instead of going from -5 to +5, since you're basically subtracting off this negative, it's going to have an extra factor of y involved. You can double what's happening here. So you go 2 pi instead of just pi, and then you go from 0 to 5. So you don't even have to plug in the 0. Things will be hunky-dory for you in a second then. And so this thing becomes 20 plus square root of 25 minus y squared, that quantity squared. So what the heck does that thing look like? I'm going to just write out 20 squared plus 2 times 20. And you'll see why I'm not actually simplifying this just yet. Times the square root of 25 minus y squared, and then plus 25 minus y squared. That's the first portion. We got to subtract off that second sort of portion here. So we get minus, and we get 20 squared again, and then we get minus 2 times 20 times the square root of 25 minus y squared. And then last but certainly not least, you get the plus the 25 minus y squared. And I'm sorry for running out of room there, and then we have a dy. I'll write it down there. Yippee-ki-yay. So now we have 20 squared is gone because you're subtracting that second piece. 25 minus y squared, and then you subtract off 25 minus y squared. That's gone. So you might say, oh, the whole thing goes. No, it's not that much of a fire sale. You have a minus and minus that makes a plus. So that makes this thing becomes 2 pi times the integral from 0 to 5. And then we have, what is it? So 2 and another 2 makes 4. So you have 4 times 20 times the square root of 25 minus y squared. And by the way, that 25 came from, remember, it's the little 5 squared. So I might convert that back real quick just for kicks to let you see what's happening here. So this is 5 squared minus y squared. So you can pull out the 4 and the 20 and all that jazz. So you have, I'll leave it as 8 pi times 20, the integral from 0 to 5 of square root of 5 squared minus y squared, and then dy. But if you remember, well, what the heck is this thing? Well, notice we have an integral from 0 to 5. Instead of putting x, I'll put y down here. I know this seems a bit funky, but hopefully it'll make sense in a second here. So if you have 5 squared minus y squared, that's square root. If I put y on this axis, that means that we have essentially the top portion of a circle. But our integral is only going from 0 to 5. And so we're shading in this. So this, without even integrating, this is a quarter of a circle with radius 5. So this should be 1/4 pi times our radius, which in this case our radius is 5 squared, right? So this whole thing equals 8 pi times 20 times 1/4 pi times 5 squared. Okay? And so if you take a look, we can simplify that a little bit. And what you end up getting is you have the 1/4 and the 8 that cross off and make 2. You have pi and another pi, and so that makes pi squared. So you have 2 pi squared, right? And then we have 20, which was our bigger radius essentially, and then 5 squared, which was our little radius. And you could check and see if this holds in general, right? Notice the 2, the pi squared, that shouldn't actually play a role at all. It's the only things that are really playing the big factors here are that 20 and that 5 squared. So you can start to change that for any general r and little r, I guess you could say, that you want to have happen. So hopefully that makes sense in terms of how this torus volume works. Yeah, go ahead and give it a shot and see what happens. There's actually, once again, I actually use the fact of what the graph looks like. You can integrate this another way. You could do y equals, this would be 5 sine theta, then dy equals 5 cosine theta d theta. And you could go through the trig substitution integral and go through it that way. There'll be another method that we'll learn, and then if you really want to learn a method to cut down your time, it's theorem of Pappus. Okay, that cuts down a lot of time. Now, on a side note, a lot of people say, well, why the heck do we need to know this? And I'll give you an idea. All this stuff, we're just taking slices of some general piece as to what's going on. So in this one, we were taking some general slice in the middle somewhere and kind of seeing what did our circle look like, what happened here, right? This slicing idea, when you think of CAT scans and stuff like that, they try and build with slices, build the whole image of a CAT scan. And so it does have a lot of practical applications when it comes down to it. So it's something to take in mind when you're doing this stuff. You're going to start to see more and more applications of these integrals and get into some fancy stuff as well. So I don't see any more questions. If there are, just let me know. I'll be happy to answer them. And then please post in the YouTube live discussions and then also the other discussions as well, and I'll try, and that's where I take a lot of the problems from there and try and just change out some numbers and give you a general idea as to what's going on. So hope you all have a good one. Hopefully this helps, and I will see you next time.